Imagine for a moment that you are standing on the edge of a waterfall, but this isn't a waterfall made of water. This is a waterfall where space itself is pouring downward into an invisible drain. You are floating in your high-tech spacesuit, watching the stars behind you, but in front of you there is nothing but a perfect, circular ink-black void. This is the event horizon of a black hole, the point of no return. If you go 1 inch further, the laws of the universe as you know them will cease to function. Your past, your future, and the very atoms that make up your body are about to enter a region of the cosmos that physics simply cannot explain. We have spent decades theorizing, calculating, and even photographing these celestial monsters. Yet the moment we try to describe what is actually happening inside them, our best scientific equations literally break. They start spitting out infinities and nonsensical results. Today, we are going on a journey beyond that dark curtain to explore the most forbidden territory in existence. We are going to find out what is actually inside a black hole and why the answer is currently tearing the world of physics apart. To understand the inside, we first have to understand the threshold. The event horizon is often described as the surface of a black hole, but it isn't a solid surface. It is a mathematical boundary. It is the distance from the center where the escape velocity required to leave exceeds the speed of light. Since nothing can travel faster than light, nothing can come back out. This creates a one-way trapdoor in the fabric of reality. But here's where things get weird for the person falling in. If you were falling into a supermassive black hole, like the one at the center of our galaxy, you might not even realize you had crossed the event horizon at first. Because the black hole is so large, the gravitational difference between your head and your feet is relatively small at the boundary. You would just feel like you were floating in space, watching the universe outside get smaller and smaller, compressed into a bright circle of light behind you. But while you feel fine, time itself is beginning to fracture. According to Einstein's theory of general relativity, gravity warps time. The stronger the gravity, the slower time moves. As you descend toward the center, an observer watching you from a distance would see you slowing down. To them, you would seem to freeze at the edge of the event horizon, turning redder and redder as your light is stretched out, until you eventually fade away into nothingness. They would never actually see you fall in. But from your perspective, time is moving perfectly normally. In fact, if you looked back out at the universe, you would see stars flickering and dying in fast forward. You would see the entire future of the universe play out in a matter of minutes because your time has slowed down so much relative to the rest of reality. You are effectively falling out of time itself. As you move deeper into the black hole, the real trouble begins. This is where we encounter the phenomenon popularly known as spaghettification. Even though you felt fine at the event horizon, as you get closer to the center, the gravity becomes so intense that the pull on your feet is significantly stronger than the pull on your head. This tidal force starts to stretch your body into a long, thin strand of plasma, just like a piece of spaghetti. It sounds like something out of a cartoon, but it is a brutal reality of high-gravity physics. Your molecules, then your atoms, and finally your subatomic particles would be pulled apart until you are nothing but a stream of information flowing toward the core. But where is that stream going? In the classic model of physics, every black hole leads to a singularity. This is a point of infinite density and zero volume. Imagine taking the entire mass of a star 3 times bigger than our sun and crushing it down until it is smaller than a single grain of sand, then smaller than an atom, and then smaller until it has no size at all. This is where Albert Einstein's math stops working. In mathematics, you can't divide by zero, but that is exactly what a singularity demands. It is a place where space-time curvature becomes infinite. If the math says something is infinite, it usually means the theory is incomplete. It means we are missing a pieces of the puzzle. The singularity is the ultimate no-go zone for scientists because it suggests that at the very heart of these objects, the universe as we understand it simply ends. However, many modern physicists believe that singularities don't actually exist. They think singularity is just a word we use for we don't know what's happening here yet. One of the leading alternative ideas is that the center of a black hole isn't a point of infinite density, but a Planck star. This theory comes from loop quantum gravity. It suggests that once matter is crushed down to the smallest possible size allowed by the laws of nature, known as the Planck length, it can't be crushed any further. Instead of collapsing forever, the matter creates a sort of quantum pressure that pushes back. Imagine a spring being compressed so tightly that it eventually reaches its limit and wants to bounce back. A Planck star would be an incredibly dense core that is technically trying to explode outward, but because gravity is so strong, that explosion is frozen in time. From the outside, it looks like a black hole. From the inside, it's a temporary state of extreme density waiting to rebound. But let's get even more experimental. Some theorists suggest that black holes could be gateways. If you have a rotating black hole, which most of them are, the singularity isn't a point, but a ring. This is called a Kerr singularity. Mathematical models suggest that it might be possible to pass through the center of this ring without being crushed. Where would you go? This leads us to the concept of Einstein-Rosen bridges, better known as wormholes. The idea is that a black hole might be connected to another point in space-time through a tunnel. On the other end of this tunnel would be the opposite of a black hole, a white hole. While a black hole sucks everything in and lets nothing out, a white hole would be a region of space that gushes matter and light out and lets nothing in. You would fall into the black hole in our universe and be ejected into a completely different part of the cosmos, or even a different universe altogether through a white hole. While white holes have never been observed, they are perfectly valid solutions to the equations of general relativity. However, we can't talk about the inside of a black hole without addressing the biggest fight in the history of modern science, the black hole information paradox. This is the conflict that pitted Stephen Hawking against almost every other quantum physicist for decades. It starts with a simple rule in quantum mechanics. Information can never be destroyed. Every atom, every state of energy, and every bit of data about how a particle is configured must be preserved in the universe. But Stephen Hawking discovered that black holes aren't actually eternal. They leak a tiny amount of radiation, now called Hawking radiation. Over trillions and trillions of years, a black hole will eventually evaporate and disappear completely. Here is the problem. If you throw a book into a black hole, and then the black hole evaporates, what happened to the information in the book? If the information is gone, then quantum mechanics is wrong. If quantum mechanics is wrong, our entire understanding of how atoms and chemicals work falls apart. But if the information stays inside, where does it go once the black hole is gone? This paradox led to some of the most mind-bending theories ever conceived. One of the most popular is the holographic principle. This theory suggests that the inside of a black hole might not exist at all in the way we think it does. Instead, all the information about the objects that fall in is smeared across the two-dimensional surface of the event horizon, like a hologram. Just as a two-dimensional credit card chip can hold three-dimensional information, the surface of the black hole might be a record of everything inside. If this is true, it suggests that the entire three-dimensional universe we live in might actually be a projection of information stored on a two-dimensional surface at the edge of the cosmos. Another wild solution to the information problem is the firewall hypothesis. This theory suggests that the event horizon isn't a smooth transition at all. Instead, quantum effects turn the boundary into a literal wall of high-energy particles. The moment you touch the event horizon, you would be instantly incinerated. This would solve the paradox because the information never actually enters the black hole. It is destroyed and converted into heat at the surface. But this also breaks Einstein's general relativity, which says that a person falling into a black hole shouldn't feel anything special at the horizon. So we are stuck. Either Einstein is wrong or quantum mechanics is wrong. There is no middle ground that satisfies both. This is why black holes are the ultimate laboratory for the future of science. They are the only places in the universe where gravity is strong enough and the scale is small enough that we need both theories to work together, and they currently refuse to do so. If we venture even deeper into the speculative, some physicists like Nikodem Poplawski have proposed that every single black hole contains an entire baby universe. This is the theory of torsion. It suggests that when a massive star collapses, the spinning motion of the matter creates a repulsive force that prevents the formation of a singularity. Instead, the matter expands inside its own new spacetime. If this is true, then our own universe might actually be the interior of a black hole that exists in a parent universe. Every time a black hole forms in our galaxy, a new universe is born on the other side. This creates a cosmic family tree, an infinite chain of universes nesting inside one another like Russian dolls. It's a beautiful and humbling thought. It would mean that instead of being a place of destruction, a black hole is actually a place of creation. But let's bring it back to what we can actually see and measure. When we look at the gargantuan black hole M87 star, which was the first one we ever photographed, we are looking at a shadow. We are seeing the light of the accretion disk being bent and distorted around the event horizon. That light is what scientists call a photon sphere. It is a region where gravity is so strong that photons, particles of light, are actually forced to orbit the black hole. If you were standing at this distance, you could look straight ahead and see the back of your own head, because the light from your hair would travel in a full circle around the black hole and come back to your eyes. It is a place where vision itself becomes a loop. The deeper you go, the more the coordinates of space and time actually swap places. Outside a black hole, you have freedom of movement in space. You can move left, right, up, or down, but you have no freedom in time. You are always moving toward the future. Inside the event horizon, calculations show that these roles reverse. The center of the black hole, the singularity, is no longer a location in space. It becomes a location in time. It is your inevitable future. Just as you cannot stop yourself from moving toward tomorrow, a person inside a black hole cannot stop themselves from moving toward the center. No matter which way you turn, or how hard you fire your rockets, every direction leads to the core. Space itself has become so warped that there is literally no path that leads away from the center. This leads us to the concept of black hole interiors as Krolust zones. Because of the extreme time dilation, it's possible that the internal life of a black hole is over in an instant, even if from the outside it takes quadrillions of years to evaporate. To an observer inside, the universe's beginning and end might happen simultaneously. You are effectively walking through a doorway into a part of the universe that is disconnected from the causal flow of everything else. It is a pocket of reality that has opted out of the standard cosmic timeline. So why does the answer break physics? It breaks physics because it forces us to confront the fact that our two most successful theories are fundamentally incompatible. General relativity is the big theory. It handles stars, galaxies, and the shape of the universe. Quantum mechanics is the Proust-Small theory. It handles atoms, light, and subatomic particles. They are like two different languages that describe the same world. For most of history, this hasn't been a problem because big things are rarely small, and small things are rarely heavy. But a black hole is both. It is a star that has been crushed into the quantum scale. When you try to use both languages at once to describe the center of a black hole, the words stop making sense. This is the search for the EE theory of everything, or quantum gravity. Until we can successfully explain what is at the center of a black hole without the math breaking, we cannot say we truly understand how the universe works. What is actually inside a black hole might be something we are currently incapable of imagining. It could be in fluff of high-dimensional strings, as suggested by string theory. It could be a fuzzball, which is a dense mass of energy that has no clear horizon or singularity. Some even suggest that black holes are just dark energy stars that prevent the collapse of the universe. The diversity of theories is a testament to how little we actually know. We aren't just looking at a star. We are looking at the boundary of human knowledge. Every time we learn something new about black holes, we find 10 more questions that we didn't even know how to ask. Think about the scale of these things again. The supermassive black hole at the center of the galaxy TON 618 is so large that its event horizon could fit 11 solar systems side by side. Falling into something that large would be a journey that takes hours, even as you are being pulled at unimaginable speeds. During those hours, you would be the only human being in history to see the true face of the universe. You would see the curved geometry of space-time in its most extreme form. You would see light from across the cosmos being concentrated into a shimmering ring of fire. You would see the secrets of the universe, and you would be unable to tell anyone what you saw. Scientists are afraid of black holes in a metaphorical sense because black holes represent the death of predictability. If information can be lost, if math can fail, if time can stop, then the universe is far more chaotic than we want to believe. We like to think that we live in a clockwork universe where every cause has an effect and every problem has a solution. Black holes suggest that there are regions of space where the clock just breaks. They are the glitches in the matrix. They are the places where the creator of the universe, if such a thing exists, didn't finish the code. But these monsters are also necessary. Without the supermassive black holes at the centers of galaxies, those galaxies might never have formed. They act as the gravitational anchors for everything we see. They regulate the birth of stars. They recycle matter and energy on a scale we can barely fathom. We are here because of them, even though we can't survive near them. They are the dark hearts of our cosmic neighborhood. As we look toward the future, we have new tools to peer into the dark. Gravitational wave observatories like LIGO are literally hearing the ripples in space-time when two black holes collide. These ripples carry information from just outside the event horizon, giving us clues about the mass, spin, and behavior of these objects. Perhaps one day a gravitational wave will carry the echo of the interior, a signature of what lies beyond the veil. Until then, we are left with our theories and our imaginations. We think of black holes as payholes or voids, but it's more accurate to think of them as the most full places in the universe. They are packed with the history of everything they have ever consumed. Every photon of light, every planet, and every star that has fallen in is still there in some form, added to the mass and the mystery. If you could somehow peer through the horizon and survive, you wouldn't see nothing. You would see the most intense concentration of reality possible. You would see the universe pushed to its breaking point. The answer to what is inside a black hole breaks physics because physics is a human invention, and a black hole is a fundamental truth of nature. Our math is a map, but the black hole is the territory. Sometimes the territory is too complex for the map. This doesn't mean the territory is wrong. It means we need a better map. The generations of scientists to come will spend their lives trying to draw that map, trying to find the bridge between the quantum and the cosmic. And when they do, the secret of the black hole will finally be revealed. It might be a new universe, a wormhole, a frozen star, or something so simple and elegant that we'll wonder why we didn't see it all along. Until that day, we can only look at the stars and know that out there, scattered across the darkness, are millions of these invisible gateways. They are the guardians of the universe's deepest secrets. They are the places where the light ends and the mystery begins. Every black hole is a reminder that no matter how much we think we know, the universe will always have a way to surprise us, to challenge us, and to remind us that we are just small observers in a vast, dark, and beautiful theater. So the next time you look at a picture of a black hole, don't just see a circle of darkness. See a challenge. See a question that is yet to be answered. See the place where physics ends and the future of science begins. Because what is actually inside a black hole may be the most important discovery we ever make. It is the key to understanding the beginning of time, the end of the universe, and the fabric of everything in between. We are standing on the edge of the waterfall, looking down into the mist, and even though we can't see the bottom, we have never been more excited to find out what's there. The journey into the black hole is the journey into the ultimate unknown, and that is where the best stories always begin. As we conclude this deep dive, keep in mind that the very atoms in your body might have once been part of a star that collapsed into a black hole in a distant galaxy. We are part of this cycle of collapse and expansion. The energy inside a black hole is the same energy that fuels the stars we see at night. We are connected to the dark just as much as we are connected to the light. The black hole isn't an other. It's a part of our home, a part of our history. And maybe, just maybe, it's a part of our future. Whether it's a gateway to another world or a final destination for matter, the black hole remains the ultimate icon of the power and scale of the cosmos. Keep looking up. Keep asking what if, and never be afraid of the dark, because it's in the darkest places that we often find the brightest truths. We are just getting started in our quest to understand these giants, and the most exciting breakthroughs are still waiting for us, safely tucked away behind that horizon of no return.